All right, and we're recording now. Not going off the OpenStax this time here. Um, Going off of Calculus Early Transcendentals by Stewart. And don't worry, I'll post all the working here as well. So let's just start off here. We want to see if this sum converges. All right, so go ahead and start here with this simple one here. Over n plus 3 to the n. And it would be nice if that n wasn't there, but it doesn't really matter because I have a hunch that this one converges. Because 3 to the n grows faster than n. So we're going to note here that 1 over n plus 3 to the n, I'm going to claim as asymptotic to 1 over 3 to the n. So it behaves the same, more or less. I could do a direct comparison if I wanted to. I know that eventually 3 to the n dominates n. Okay. So, and 3 to the n is positive. Alright, how do I want to do this? Well, I don't really want to use the direct comparison test. I just want to use limit comparison. I'm going to compare against 1/3 to the n, and you'll probably see why I'm choosing that one here. So I'm going to check this limit here. My reference series, my reference sequence, rather. Actually, how do I want to do this? So an divided by bn does this give me what I want? Yes, it does. Okay. So we'll use some exponent rules here. It doesn't really matter what you call an and bn here. So I have the limit as n goes to infinity of n over 3 to the n, and then plus, when I multiply the other term out, 3 to the n over 3 to the n is just 1. And now you just use some manipulations from... just think about the relative growth. Okay. You don't necessarily have to, like, really show... You don't have to show it rigorously, but you can just use your Calc 1 intuition here. Or if you use L'Hopital's rule, but be careful, because the derivative of 3 to the n is 3 to the n times natural log 3. So, but anyway. What we'll get here is that this limit is 1, since n over 3 to the n goes to 0. Since the limit is 1, is positive, and you'll see why I chose the reference series I did, because this sum here converges because it's geometric. Common ratio less than 1 in absolute value. Given the sum converges as well. So limit comparison is just good if I like look at the highest order terms, really the most dominant terms. Okay, so that's just an example of how to use the limit comparison test there. All right. Let's take a look at some other ones here. Where are we looking at? Like this track here. Let's look at another one. And here we go. This one's good too. 2n plus 1 to the n over n to the 2n. Okay, so for this one, I see an n in the exponent, so I'm already thinking root test. All right, so root test, we just take the 1 over n power, the nth roots, and then take the limit. And I should really look at absolute values, but because all the terms here are positive, I don't really need to do that. So look at this. So 1 over n power. And remember, power to a power makes it a superpower. So just multiply the exponents. So n times 1 over n is 1. So I have 2n plus 1 on top. And in the denominator, I'll have, well, n to the 2n to the 1 over n. 2n times 1 over n is 2. So I have n squared. Now you should be able to see that this is bottom heavy because I have a quadratic in the denominator that grows faster than linear. This limit is 0. But if you want to verify this for yourself, separate the fraction, right? I'll get 2n over n squared plus 1 over n squared. Second term goes to 0. First term simplifies to 2 over n, which goes to 0. So this limit is 0. Okay. So because this limit is 0, so since the limit is less than 1, the sum converges by the root test. That's how you use the root test. Very simple. Let's do this next one here. This one's also quite simple. Number 3. It's an alternating series. And when I see an alternating series, my first instinct is to use the alternating series test. And so I'm going to use the alternating series test here. So my helper sequence is n over n plus 2, which is positive. And decreasing. You can check decreasing in a couple of different ways. Here, n over n plus 2, do some long division, you get 1 minus 2 over n plus 2. And you can see that the difference is the thing that you're subtracting gets smaller. Okay. Oh, actually, no, it's not decreasing. This is not decreasing. We can't use the alternating series test here because that's not decreasing. Yeah, it's not decreasing. It's actually increasing. You'll have, if you separate this out, you get 1 minus 2 over n plus 2. And because the differences get smaller, you're subtracting less and less, so it's actually increasing to 1. So you can't use the alternating series test here. But a possible candidate here is, I mean, I do have a hunch that this might diverge. I think it diverges. Let's test for absolute convergence. Let's just test for absolute convergence. So we're going to take the absolute values here. And so that just removes the alternating bit. And check, okay? Now, okay, there we go. This diverges because if we take the limits, okay? The limit of this thing is 1, so the sum diverges. Okay, there we go. The sum diverges, okay? Very easy to see. Let's see. All right, so yeah, that one's pretty straightforward. Let's go on to a different one here. I'm not going to go in chronological order. But I really like the look of 5 here. I like the look of 5. Let's take a look at that one. N squared times 2 to the n minus 1 over minus 5 to the n. Okay. And for those of you that are still with us here, thank you very much for sticking through the stream. I know it's a long one. A VOD will be released. Okay. So let's see. What do I want to listen to? Yeah, let's put on some Spyro. All right. Let's look at the original. There we go. Okay, I'm gonna like put it back to the beginning. There we go. I kind of part of me wants to use a ratio test here. I mean, because ratio test is the most powerful. Let's do a bit of experimenting with the terms here. Let's look at the corresponding sequence. I'm gonna go ahead and I have a 2D n minus 1, so I am dividing by 2 here. Then I have minus 1 to the n, then minus 5 to the n. And let's see, this gives me... Well, I can just move to minus 1 to the n up to the top. No, that's a plus. So I can move the minus 1 to the n up to the top. And it almost looks geometric. It almost looks geometric. So, yeah, I think we're going to go ahead and do the limit comparison test here. I have a feeling it's geometric, but for limit comparison, I need a positive sequence, so I would have to take absolute values first. Ratio test is probably a good... Actually, no, let's just do the ratio test. Let's use the ratio test. I think it's the best choice here. So we have n plus 1 squared over 2 times minus 1 to the n plus 1 times 2/5 to the n plus 1. Okay, and then times the reciprocal, so... yeah, I should be a little careful here. Let me write it like this instead. 5 to the n plus 1. Okay, there we go. So now multiply by 2 times 5 to the n over n squared times minus 1 to the n times 2 to the n, take absolute values. So all the minus stuff drops. Anyway, because it's an absolute value. I got 2's that drop out. And it looks like I have n plus 1 squared over n squared times a 1 over 5 left over. The 1 over 5 I can pull out of the limit. And I just have n plus 1 over n squared. And that definitely goes to 1. So this whole limit is 1/5. And so, by the ratio test, this sum converges. In fact, the sum converges absolutely. Okay, we showed absolute convergence, that implies regular convergence. Absolute convergence is stronger, remember that. This next one's pretty good for the integral test. Although, you really don't want to use the integral test a lot. There's a lot that you have to show for it. This probably could... Whoops. I think this probably can be shown through comparison, but I don't quite see how to do the comparison. Well, I know n is bigger than log n. So 1 over n is smaller than... so yeah, that may not work. So let's just use the integral test. I don't want to, but we just may as well. And you'll see why the integral test can be a pain in the ass. So, pass this to a continuous function. This is positive. Let's make sure. Yeah, log 2 is positive. Now we just have to take the derivative. So I'm going to do this by means of the power rule. And the chain rule, obviously. And the product rule as well. So minus x square root log of x minus 2 times... Okay, first times the derivative of the second. Square root of log x, the derivative is 1 over 2 square root log x. So, well, 1 over 2x square root log x. That's some power rule, a product rule nonsense. Plus second times the derivative of the first. So there's a lot here. Well, when I square that, I get x squared log x down there. And then we'll have 1 over 2 square root log x plus square root of log x. All right, so we just need to show that this is negative, okay? So, in fact, x squared log x is positive for x in the interval 2 to infinity. And log x is positive in that interval. Well, we have positive number times plus positive number, that's a positive number, times a positive number, with a minus sign out there. So the derivative is negative. So we showed that it's positive and decreasing, and continuity kind of follows, but we have the decreasing bit, now we can use the integral test. So before you even do the integral, you have to verify this. This is why this is nonsense half the time. I would save it as the last thing you would do. So 2 to infinity, 1 over x square root log x. I'm going to use u equals log x, and I'm not going to go ahead and formally pass to a limit yet. So u equals log x, du equals 1 over x dx. So we have the integral from log 2 to infinity, because as x gets large, log x gets large. What do I have here? 1 over square root u? Yeah. Alright, 1 over square root u. Now you just do some power rule stuff. And you should see that this integral diverges. As the limit as t approaches infinity of 2 square root t minus 2 square root log 2 is infinity. So since the integral diverges, sum also diverges. Okay, so that's the whole thing with the integral test. Okay. I want to do some stuff with factorial, so let's do number 8. Probably good exercise here. Switch back to the black pen. And then thank you folks for sticking around. Okay. All right, so I want to do 8 here. We have 2 to the k times k factorial over k plus 2 factorial. And I want to see if this converges or not. I think the best way to go about this is just use a ratio test because I see factorials. So let's just go ahead and do that. And everything's positive, so I don't necessarily need the absolute value. So 2 to the k plus 1 times k plus 1 factorial divided by k plus 3 factorial. Multiply that by the reciprocal. And then 2 to the k times k factorial. Okay, so let's remember the recursive nature of the factorial. Obviously, you can see that I have the 2 to the k's. Some of them drop, and I have the 2 left over. And now let me put some stuff together here. K plus 1 factorial over k factorial. K plus 2 factorial divided by k plus 3 factorial. Now, by the recursive nature of the factorial, k plus 1 factorial divided by k factorial is just k plus 1. And of course, when you take reciprocals, you get a similar result. Okay? So here, I'll have the limit as k approaches infinity of 2 times k plus 1. That's what I have left over in the numerator. And the denominator, I have a k plus 3 left over. And I feel like something should have... I feel like something neat should have happened here. Ah, nope. So in this limit here will actually be 2 if you do the comparisons. So the sum diverges. Okay. So yeah, I want to do another one with factorials just so that we can all see how this works out. And that's 13. Okay. So let's see here. Again, I see factorial, so I'm just going to use the ratio test. One could argue you could also use the root test, but it's going to be a little messy because you have to use a Stirling approximation with the factorial. So just do the usual ratio testing here. All right. I am going to have a 3 left over there. And then by the recursive nature of the factorial, n factorial over n plus 1 factorial, that's just going to be an n, 1 over n plus 1. So I have 3 times n plus 1 times, let's see, n plus 1 squared over n squared. One of those n plus 1s will drop. And I can see that this goes to 0. And so the sum converges. Fun time. Okay. See, how many have I done here? 1, 2, 3, 4, 5, 6, 7 already. Nice. Oops. Not really a lot of other nice ones here to choose. Let's see here. Maybe 18's another good one. Okay, then I think I'll go back and work a couple of telescoping sums. It's minus 1 to the n minus 1 over the square root of n minus 1. So this one's alternating, and looks like I do have a helper sequence that's positive and decreasing with limit 0, so I can use the alternating series test. So set bn to be square root of n minus 1. So note that bn goes to 0. So it has limit 0. It's positive because the square root is positive. Okay. Now we gotta check decreasing. And that's probably gonna be a bit hard to do. You can use derivatives, but I'll show how to do it with inequalities. So if I have j less than k, we'll agree that the square root of j is less than the square root of k because square root is an increasing function. And then I can subtract 1 and the inequality still holds. So subtract 1 across, I still have the inequality. Now when I take reciprocals, okay, I have 1 over square root j minus 1 is now greater than 1 over square root k minus 1. Okay, remember that the taking reciprocals reverses the order of inequalities. But what does this really say? If j is bigger, if j is smaller than k, then what I have here now is that this is saying that the term bj is bigger than that of bk. So this is decreasing. So we know that the sum converges by AST, by the alternating series test. So the sum converges by the alternating series test. Now, okay, for absolute convergence, we want to check for absolute convergence. Okay. Take absolute values. Which just removes the alternating bit. Okay, but this should look familiar. This is close to a p-series where p is equal to 1/2. And by the p-series test, okay, if the power p is less than 1, the sum diverges. Okay, so we can show that. Okay, so we'll use limit comparison against 1 over square root of n, which is not summable. Okay, so it's not summable, and you can clearly see, right? Take the limit here. I do 1 divided by the other. It doesn't really matter which way I do it. That limit is 1. Okay. So the sum converges conditionally. Not absolutely. Okay, so that's just how you figure that one out. Excellent. I want to do a couple of let's see here. I want to go back and look at a telescoping sum. All right, so let's see here. We're gonna look at the sum here from n equals 2 to infinity. This is similar to a question we had in the summer. So, you should notice that the summands look a little funky, but if you realize that you can factor, the hint here is partial fractions. Okay, so we use partial fractions here. Okay, so I can factor the denominator is n plus 1 times n minus 1. So you see that the lag, okay, in the indices is 2. Okay, so something's going to happen here. So we'll have a number over n plus 1 plus a number over n minus 1. Okay, so we do the partial fractions work. And if I'm clever enough here, I get that, let's see here. A should be minus 1/2. No, A is minus 1. Because negative 2 divided by negative 2 is a negative 1. And B is a positive 1. Okay, so now my sum gets written as the following. So we have 2 over n squared minus 1. This gets factored as minus 1 over n plus 1 plus 1 over n plus 1. Okay, and the idea here is that you need to expand and explore, okay? So we need to look at the partial sums, okay? So we're going to consider the partial sums. Okay. So let's see. We're going to check the partial sums SK. So SK is the sum from n equals 2 to k of that thing. Oh, wait a minute. That should be a minus up there. Okay. And minus 1. So we're just going to expand and explore, okay? So n equals 2 gives me minus 1 over 3 plus 1. Then n equals 3 gives me minus 1 over 4 plus 1 over 2. N equals 4. Let's see, minus 1 over 5. And I'm just going to plug in like a lot of reference numbers here. Okay, just so that we can see the pattern here. And then hopefully we kind of see what happens. So let me label here. That's for n equals 2, 3, 4, 5, 6. Okay, and now I'll go do the k minus 1 stage. Or actually, I'm going to do the k minus 2 stage. So this is k minus 2. K minus 1. And then the k stage. So let's label that in here. So yeah, the partial fractions here is because I want to be able to easily get a pattern here, and the idea is if I break this up into a simpler sum of fractions, okay, you should probably already see like some of the cancellations in the head of the series here for the partial sums. So let's see, this is for k minus 2 stage. This is k minus 1, and that's for n equals k. So I did the partial fractions because if we notice here, some terms survive and some terms die. So notice here I have a minus 1/3 in the n equals 2 stage and plus 1/3 in the n equals 4 stage. So those vanish. Okay, I have a 1/5 that goes away as well from the n equals 4 and the n equals 6. Okay, and let's see. I think in the head, I think that's all that goes. Because let's see here. We have let me see. Let's see if we can make sense of this. Minus 1/3, minus a fourth, minus a fifth. So which terms survive? Well, I know the 1/4 goes away. Okay, minus a fourth plus a fourth. And then if I like wrote out more terms, right? If you explore with like specific values of k, you'll see like which terms will survive for real. The minus 1/6 will cancel with something here, so we'll minus 1/7. But in the tail, notice that I have minus 1/k minus 1, and then a plus 1/k minus 1. Okay, and let's see here. It's going to appear that I'll have the k minus 2 term cancel with something in here. And same with the k minus 3. So which ones survive? 1 plus a half minus 1/k minus 1/k plus 1. Okay, so if I look at this, sk is equal to 1 plus a half, which is 3/2, minus 1/k minus 1/k plus 1. So now that I have an expression for the partial sums, we need to take the limit of the partial sums, because a series converges when the limit of its partial sums exists. Okay, so now we have, whoops, no, y'all can't see that. Now the limits as k goes to infinity, okay, of the SKs, well, notice those last two terms in the sum, right? In the partial sums, right? The 1/k and the 1/k plus 1, those go to 0 as k gets large. So the sum converges. Three over 2. Okay. So this is just a quick and dirty way of like how to do the partial sums here, using partial fractions. Okay. This would be a little easier if we had just like 1/n times n plus 1, but this is the general idea. I want to do one more. In fact, I'll do one where like the lag is actually like 1 instead of 2. Hmm. I really want to see if there's another one in this book. Okay, no, I'd have to like go a little further. So I would encourage to look back at my course. Well, I don't have that video, but I do have the old video out. But the idea is just that you need to telescope. Here. In fact, let's just go ahead and look at a bonus example. I'll just make one up here. Right, so this one looks like partial fractions, again. So I'm going to go ahead and decompose this into partial fractions. Okay, so a number over n plus 3 plus a number over n plus 2, clear to fractions. Okay. If I set n equal to -2, I get that b is 12. And n equal to -3, a is -12. So we're going to go ahead and write this just like we did before. And if you know how to program, like, definitely write this as a for loop, and you'll see that the sum converges, like, I mean, probably slowly, but it'll converge. Well, so now we're going to do the same thing. And I've done the same stupid mistake again. All right. So consider partial sums sk again. You'll probably see the patterns emerge again. So for n equals 1, we get minus 12 over 4 plus 12 over 3 minus 12 over 5 plus 12 over 4 minus 12 over 6 plus 12 over 5. Once you do some exploration, you'll see those patterns. For k minus 1 stage, you'll have k plus 2, k plus 1, over k plus 3 plus 12 over k plus 2. Okay? Which terms die? These here, these here, these here. That'll die. Those terms die. That one dies with something else. The only ones that survive are there and there. So the partial sum here, sk, is 12 over 3, which is 4, minus 12 over k plus 3. But now when you take limits, yeah, that the sum converges to 4. Man, my hand hurts. All right. Not a lot of people left in here, but thank you all for coming. We got one more part to go, and that is power series. Okay, it's power series I'm going to be talking about last. I'll do a couple with intervals of convergence, generating power series, and then a couple of Taylor expansions. Okay, so we'll go ahead and take our last break. All right, we'll come back and finish it out with power series.